Okay. Mikrofon okay. Teşekkürler. So, okay, we are starting week 4 in deep learning, and we are still trying to cover the fundamentals. And today we are going to start convolutional neural networks. But let's remember what we have seen in the last week. We looked at the artificial neuron models, specifically perceptron, and we looked at its learning rule, and we discussed why it was working, although it was not gradient descent. Then we combine these artificial neurons into graphs, and we call them multi-layer perceptrons, MLPs. We studied backpropagation. We did 2 examples by hand. We talked on the initialization of neural networks, activation functions, and then we talked about how we can set the learning rate in practice. And of course, we talked about stochastic gradient descent. Today, we are going to look at several different topics, but I'd like to start with a funny note, but it's also real. Do you know who is Adam? So in one of the top conferences in this field, NeurIPS, in NeurIPS 2025, one of the reviewers actually wrote this review. He said, or she said, both architectures are optimized with Adam. What is Adam? I think this is a very serious typo that the author should have removed from the submission. So Adam is a learning method, learning algorithm, adaptive learning rate method. And it's widely used. It's like SGD, stochastic gradient descent. And it's very funny, right? But in a top conference, a reviewer might miss what Adam is. Some people said this comment is made because proper citation is not given. If you don't cite Adam paper and you say that we optimized it with Adam, then maybe this question is valid. Maybe that's the point of the reviewer. But anyway, we are going to learn about Adam today. So we will know who is Adam. So there are 2 leftovers from last week. One is the Colab notebook on multi-layer perceptrons, and then we stopped at the momentum. So we will cover them first, and then we will talk about adaptive learning rate methods. We will talk about how we can implement backpropagation in a modular way, because we don't want to compute the gradient for every specific architecture. There is a way to compute it in a modular way. And then we will start with CNNs. Okay. The recommended reading for this week is the Nature paper by LeCun, Bengio, and Hinton. Its title is Deep Learning. It's a very nice overview paper. I highly encourage you to read that paper. Okay, let's start with the Colab notebook. I can go from here, or let's see. Here. It was in week 3. Okay. In this Colab notebook, we are developing a multi-layer perceptron, and we will train it and test it on the MNIST dataset, which is a dataset of handwritten digits. And here you see a sample MNIST images. We have 10 classes from 0 to 9. And for each class, you have 60,000 training images. And Here we show only 10 instances, or maybe, I don't know, as many rows here, instances from each category, but this list is 60,000 rows um, in total. But for each digit, we have about 6,000 examples, okay? And there are 10,000 testing images, and each image is a monochrome image. That means there's only one channel. It's a grayscale image, and 28 by 28 pixels. So we are talking about tiny grayscale images. But you can recognize what digit that the image contains. So it is a valid image classification data set. Uh, Today, this data set is not being used to benchmark ML models because it's already 99.5+%. So it's already saturated, it is solved. But it is still being used to sanity check models. If you develop a new model, you should try on this and you should get a very high percentage accuracy. The first thing we do is to import required modules. You import torch, and then from torch, data sets, transforms, and so on. We define a device here, and this line makes sure that if there is a GPU available, then device is set to the GPU, otherwise CPU is used. Downloading of the dataset is very easy through the datasets package. You just set train data is equal to dataset.mnist and so on. It will just download it for you. You separate the train and test data by the train flag here. If you say train is equal to true, it will download the train set. Otherwise, it will download the test set. There is a transform applied to the data. If you notice, transforms.toTensor. I'm not sure if it's visible from there. Maybe I can make it bigger like this. Okay. So that data set is downloaded. About the tensor transformation. So the PyTorch networks expect a tensor as input with dimensions n times c times h times w, where n is the batch size, c is the channel size, h is height, w is width. Normally, an image, if you load it to memory, you will see that it's height times width times channel multidimensional array. But to tensor transformation moves the channel dimension to the beginning as needed by PyTorch. Next, we define the data loaders, and this is where the shuffling of data and splitting the data into batches is done. So the data loader actually splits the whole data set for you in sizes of batch size. And then if you say shuffle through, it shuffles the data set. And I believe it shuffles it at every epoch, at beginning of every epoch. So this is where the true stochasticity happens in stochastic gradient descent. If you don't say shuffle through, then every time through multiple epochs, you will see the same batches again and again. That should also work, but probably suboptimally. Okay, next, here we define the neural network, and that's probably the important part. We define two fully connected layers. Sorry. Here we define two fully connected layers, FC1 and FC2, and there is a nonlinearity ReLU. In the init function, the constructor, you define the layers, and in the each neural network class in PyTorch should have a forward function which defines the feed-forward information processing. And this is actually where the structure of the network is specified. So you take the input. This is coming from your batch, right? And you pass the input first through the FC1 layer, which has input size dimension in its input, and in its output, it outputs non-hidden neurons dimensional tensor or feature map, and then this passes through ReLU, which is a nonlinear activation, and then after that it passes through FC2, and then notice that we don't apply any nonlinearity on top of FC2. It's not needed because FC2, on top of FC2, the PyTorch will itself apply softmax and cross entropy. And softmax itself is a normalization, nonlinear layer. So it kind of acts like an activation function as well. Yeah, very simple MLP. One densely connected or fully connected layer, ReLU, and second fully connected layer. In the hidden dimension, we have non-hidden neurons, which is defined somewhere above. Let's see, I forgot the... okay, we will instantiate the network here where it is defined. The input size is 28 by 28. Since we are training an MLP, we don't have convolutional kernels here. That means we have to vectorize the image. So flatten the image into a single vector. And the size of that vector is 28 by 28. We are using 64 hidden neurons, and the number of classes at the output is 10. And in this line, net that equals MLP, this is where it instantiates your network. And then after we instantiate it, we move the model to the device, which is the GPU usually. Net.toDevice moves your model to GPUs, to GPU. It also, sorry. Okay, it also prints the architecture of the network for you here. Next, we define the loss function and the optimizer. As the loss function, we are using cross entropy, and this is as simple as that. See, we did lots of derivations in the last weeks, but everything is taken care of by this single line. And for the optimizers, we are using SGD here. Again, we give as the first argument to SGD what to update, and these are the models parameters, net.parameters. This is the theta that we were talking about in our mathematical notation. Learning rate is 0.001 and momentum 0.9. We will talk about momentum right after this. But simply it takes a moving average of the past gradients. 0.9 is just a parameter of that. And that's it. Next is the training loop. Here we define a training loop which will run for 5 epochs, and 1 epoch means a complete full pass over your data set, right? So 5 epochs. We are going to do this loop. Within the epoch loop, we see another loop. That loop iterates over the batches. C, it takes the enumerate train loader, which train loader is the thing that splits your data into batches. So the inner for loop iterates over your batches in your data set. So it takes the images to device and its corresponding labels to device. Here we we flatten each image into a single vector in the first line by using this dot view. vectorizes the images. And then the next lines, optimizer.zeroGrad actually resets the cache within PyTorch. It resets the gradient cache. If you don't do this, then you will have some unpredictable behavior because the gradient calculations from the previous iterations will be in the cache, and then you will be reusing them. It won't hurt too much, but this is the right thing to do, zero grad. The second line is where the model processes the input. So remember the y is equal to fx. This is that line. Output equals net of images. This is the forward pass. And then after we do the forward pass, we compute loss. Using the loss function, we defined it to be cross entropy before. And then after that, we do backpropagation. So loss.backward does that for you. It computes the gradient, and it writes that gradient into that cache. See, it doesn't return anything for you. It doesn't return, but you can take it if you want. And optimizer.step does the learning update. This is where the data is updated based on the calculated gradient. This is all actually. The other lines is just printing the progress of your training. It prints the epoch number, step number, and the loss that you have for that batch, right? You print the loss for that specific batch. Yeah. And then this is the output. See, through the epochs and iterations, in the third column, you start with 2.1 loss, and then it goes down to 0 point something. But as we said before, never just look at these numbers, always plot the training loss curve. And this is what it does. And here is the training loss curve. And then we also said, interpret the value at which your loss converges. So here it seems that the loss converges around 0.5. Now, is it a good value or bad value? How do you interpret it? You don't know? Okay.
What is our loss function?
Cross entropy. And we have 10 classes. So, remember cross entropy, we have a loop over your data examples, and we have another summation through classes, and you have the label, which is the element of a one-hot vector. So yic is either 0 or 1, and then log of qic, and this is the prediction of the model in terms of probability. Prediction of model for ith example and seed class, right? This is the prediction of the model, and we are, of course, looking at the negative of this. So this value. So if you look at the structure of this formula, yic is either 0 or 1. And for a specific example, let's say belonging to class 1, yic, the first element will be 1, the others will be zeros. That means we are looking at, so the curve was like this, right? Something like this, and this was 0.5. And this is cross entropy. This tells us that, on average, the log QIC is around 0.5. So this is where this value is where your average log of QIC is. Okay, so let's look at the plot of log. Log x here. We have to look at the minus of it. Let's see. Okay. Yeah. So log of x equals minus log of x equals 0.5 means, so it's around here, right? It means that we are getting, but okay, first, what is PyTorch using as the base of the log? Do you know? Because when I say log of x, it's base 10. But PyTorch is using E base, so that I have to plot ln. It's base E. Okay. So cross entropy loss value around 0.5 corresponds to, so if I track this line and it corresponds to around 0.6, that means on average, our model is estimating 0.6 probability for the correct class. And this is a 10 class problem. If your model was predicting at chance level, every class would get 0.1, right? Chance level prediction is 0.1. And your model is predicting 0.6. You can now interpret this value. This looks good. 0.6 probability in a 10 class problem is good, right? Because all the rest of the 9 classes will share a sum of 0.4 probability. So 0.4 over 9, so they get very small values probably. So this is how you interpret. If you have a 100 class problem, if you have a 1000 class problem, these numbers will have different meanings. But this is how you interpret, okay? So this means 0.5 means in this context, a correct prediction is getting on average 0.6, around 0.6 probability, which is not bad. But of course, as Sarp said, you should also check your accuracy on a held out data set, which is the validation set or your test set, and see how well your model does there. That's the real test actually, but this is how you monitor progress on your training set and how to interpret it. So if this converge value was around 2, let's say, that means 2 here is around between 0.1 and 0.2. This means that your predictions are very much like chance level, at chance level. So this is not good, okay? So you can interpret this values in the y-axis. You should always do that. Next, we run the train model on the testing set. This is another for loop because our test set is also split into batches. We take each batch, run the model, get the predicted labels, and we accumulate them in the correct variable. And the total variable is the number of examples that we have seen accumulated. And then the percent correct is overall correct divided by total. And this is your percent correct. So not very good, 90 point something, but we did not optimize it fully. We did not play with the design of the neural network. Usually you should get 99 plus something. Okay, any questions so far? This is how you build, train, and test an MLP. Let's go back to our slides. And now the next thing is momentum. We are going to add momentum to stochastic gradient descent. So when there is high curvature in your loss function, SGD could be slow, and it is illustrated below here. And the method of momentum accelerates it. So if you have a loss function like this, these are iso loss curves within a specific curve. If you continue on the curve, you get the same loss value. And then towards the inner circles have smaller loss values. So if you start somewhere here, due to curvature, the gradient of the loss will give you this direction, and then you take a step there, you end up here, and then you compute the minus of gradient again, it gives you this direction, and so on. You have lots of zigzags, and your convergence actually is slow because you want to reach here, but you get stuck in that very high curvature valley, and you get zigzags there. And let's see how momentum helps in this case. To understand that, let's look at the plain SGD update rule first. This is simple. You update your model parameters by the negative direction of the gradient with some step size, eta, which we call the learning rate. Now we define momentum as the exponentially decaying moving average of gradients. So we take this gradient at time t, at iteration t, and we take its moving average, and this formula does that, right? Typically, the beta values are typically 0.9 or 0.99, something like that. These are the values that people use. And this essentially takes an exponentially decaying moving average of your past gradients. So it actually takes an average, and therefore it smooths out your gradient vector. And SGD with momentum is simply this formula. Instead of using the gradient at that iteration, you just use the momentum vector, which is the average of gradients in the recent past. Okay. And why does this help? If you expand this M using the formula above, so you expand it here, and if you further expand M t minus 1, you get this. And now, finally, this is the final thing if we do two expansions. And now inspect this formula. Here you see the two terms, which has the gradient at iteration t, the gradient at iteration t minus 1. And it's obvious that we are summing them together, right? We are actually averaging them. And this averaging has the effect of, if in between these past gradients there's a common direction, that direction will be emphasized. But if there is an oscillating direction, those oscillating directions will cancel each other in the average. So if you look at this example again, so when I am here, and when the gradient gives me this direction, minus gradient, it has two components, right? It has this horizontal component and the vertical component. This is gradient at time, let's say, t minus 1. And now this is the gradient at time t. It has the, again, this vertical component and horizontal component. Now, the vertical components between two successive gradients are opposing each other. And if you average them, they will cancel each other or they will diminish their effects. But both of them has the horizontal component in the same direction, which points in this direction. So that's why this averaging has the effect of uh, emphasizing the directions where the common directions and diminishes the importance of oscillating directions, and it has the effect of if successive gradients have a common component in some certain direction, the learning accelerates towards that direction. That's why momentum works. This is just an intuitive explanation, and that's why in the vertical direction we have oscillations, but in the horizontal direction we have consistency. That's why the learning will accelerate in that direction. And this is kind of a per parameter adaptive learning rate, because now we are talking about the components here, right? A certain component gets more encouragement with momentum, but certain directions get less encouragement. That was the intuitive explanation. It is still an active area of research to explain when and why momentum accelerates SGD. This is a paper from 2023. If you are curious, you can check. It has nice theoretical results. So what I'm trying to say is it's not, the explanation I did is a very high level intuitive explanation. The reality is much more complicated and people are working on it. This is research, so you can check this paper. And also, if you look at the PyTorch implementation, I copied this from the PyTorch documentation, you will see that the implementation is slightly different. The notation is of course different, but the convention is a little bit different, but the story is the same. You are taking the moving average of past gradients and then using that to update your model parameters instead of just the gradient at that iteration. Okay, that's it for momentum. Any questions, unclear points? There is also a variation called, yes.
Actually, SGD uses many batch sample data, but any PyTorch course does not include this like many batch size or the previous one, which parameters doesn't have anything about size. So how does it decide it's actually this mini batch?
I'm not sure I understood the question well, but you are asking how PyTorch knows the batch size in the loss calculation?
It's something from the batch size, right? For
Yes.
SGD.
Yes.
But how many we can sample, for example, this occurs a minute batch in SGD.
Let's say we are sampling 32 examples.
Yes.
Then. Okay.
But there is no parameter for it anywhere, like in NLP code or in this PyTorch implementation for momentum.
So it's actually, you give it to the data loader. So PyTorch knows actually the batch size, right? You know that. It's in the data loader above. But also, now I understand your question. In the loss function, we say cross entropy loss, right? And this cross entropy loss calculates a single value, a scalar for your whole batch. Now, how can you do that? You can either sum the losses over examples, or you can take an average of cross entropy over examples in your batch. And the default is taking the average. So in the loss, you have actually, in this loss, you actually have, let's say, this is batch size. This is your loss actually. So within the loss, there is batch size. That's why when I'm interpreting this 0.5, I'm talking about on average per example loss. Okay? Does that?
So it's not like something, but averaging.
Averaging, yes.
For SGD.
Exactly. For actually any loss function in PyTorch, cross entropy loss. Let's look at that. You will see a reduction parameter here, reduction, and that's by default mean. You're taking the mean over examples in your mini batch. You can make this sum, but the interpretation will be a little bit more difficult because now you're summing, you get a large value, and yeah, usually use mean. There is a variation of momentum called Nesterov momentum. The idea is very similar, but the only difference is that in the moving average, you use the look-ahead gradient. And they say that this is numerically better and works slightly better than plane momentum. But the idea is the same. You're using the moving average of gradients. And the only difference is that whether you take the previous example and add it to the average or the current example. Okay, so the detail, I don't think it's very important, but there is this Nesterov variation. And finally, how do you use it in the SGD algorithm? It's here you compute the gradient estimate. This is as usual. You update your momentum. It's called velocity here. And then you use that momentum or velocity in updating the parameters. There's only this, that line and that line are different from plain SGD. Okay, SGD with momentum. Now, let's look at adaptive learning rate methods because they are very related to SGD with momentum, and we are going to cover these ADA-GRAD, RMS-Prop, ADAM, and ADAM-W. There are actually many more, and this is active research area, but we are going to only look at some widely used ones. Actually, these are the widely used ones in addition to SGD, but these two are necessary in order to introduce ADAM, because ADAM is just an evolved from ADA-GRAD and RMS-Prop. So finding the optimal learning rate and learning rate schedule is not trivial. Therefore, researchers have developed these adaptive learning rate methods, and this is still being researched. And momentum is kind of an adaptive learning rate method because it accelerates in certain direction and it decelerates in other directions. So it's an adaptive thing. Of course, you provide a learning rate, but you can think of it as a base learning rate on which momentum adjusts based on the moving average. Okay, so that's why it's adaptive learning rate. So far in SGD, the learning rate was global, the eta, equally applied to all parameters, but there are methods which adapt learning rate per parameter. By parameter, I mean, you know, all the learnable parameters stacked up in a vector in your model, and we called it the theta vector. And for today's models, it's huge, billion parameters, 7 billion parameters. And each of them is a parameter, learnable parameter. And these adaptive learning rate methods actually adapt the learning rates per parameter. It's very interesting. The motivation is because the cost function is highly sensitive in some directions and insensitive in others in the parameter space. Therefore, we need adaptive rates per parameter. And it might make sense to use different learning rates per parameter. And let's see the first one. The first one is from 1988, delta bar delta algorithm, and it's a heuristic method. Well, all of these are heuristic methods. And here, the delta bar delta algorithm is if the partial derivative with respect to a given model parameter remains the same sign, so that means it's consistent, it remains the same sign, then the learning rate should increase for that parameter. If it changes sign, that means it oscillates, then you can reduce the learning rate for that parameter. Okay, this is a heuristic method because you don't show that it is optimizing anything. This is just intuitive rule that you impose, and this was in 1988. And modern versions of this, the first one is AdaGrad. Let's see AdaGrad using code. It's explained much better like that. You accumulate a cache of squared gradients, okay? dx squared. dx is your gradient in your code. So the cache keeps track of per parameter sum of squared gradients, because cache is the element-wise squared of your gradient vector, and it's accumulated. Okay, so it keeps adding the gradients into this cache. And then when you're doing the update, again, we have the learning rate, of course, the gradient, of course, but the gradient is divided by square root of this cache. And what does it do? It has the effect, this effect. So weights with high gradients will have high entries in the cache because we are squaring them and adding them, accumulating them. And now we are dividing by the cache. Weights with high gradients will decrease learning rate. Weights that receive small or infrequent updates will increase learning rates. Again, we have a learning rate that is specified by the user. You provide this as the base learning rate, but AdaGrad within itself is actually using that learning rate, but it adapts it per parameter based on the squared cache of past gradients. Again, this is a heuristic rule. This is your choice that you impose. You say that if there are high gradients for a weight, then I want to decrease the learning rate for that weight. If it receives small or infrequent updates, I want to increase the learning rate there.
Doesn't additional cache explode? Doesn't it always do this?
Yes, it does. Therefore, this is not being used widely, but it's a historical important development because Adam actually uses a version of this, we will see. The second one is RMS prop, and there is no paper for it. The citation is slide 29, lecture 6, Hinton's course. So he proposed this in a slide actually, and people use this a lot. Maybe today people are using it, but it is implemented into PyTorch and other libraries. It modifies AdaGrad to use a moving average instead of complete sum. This is your question. So instead of summing all the past gradients, you keep a moving average, because summing everything in the past will probably explode, create numerical problems. It will get very large. And it's wise to keep that cache as a moving average instead of the sum. And here it does that. The current cache value is multiplied by a decay rate, and the current gradient's square is added by 1 minus decay rate. And this line basically computes a moving average. Learning rate, learning update is the same. You update your model parameters by minus the learning rate times the gradient divided by square root of cache. So it has the same logic, but just uses moving average. Now this brings us to Adam, which is today the most widely used learning update tool. It's even more widely used than SGD probably, or maybe SGD and Adam are used equally, maybe. And the idea behind Adam is it actually combines the momentum idea and the RMS prop idea. So it keeps two caches actually. The first one is moving average of past gradients, the first line. The second is moving average of squared gradients in the second line. And the learning update rule is the same as similar to RMS prop. Instead of the current gradient, you use momentum vector. This is the same in the SGD with momentum. And divided by the square root of the cache, V. And this is coming from RMS prop and ADA grad. So Adam is actually combining the momentum idea with the idea of RMS prop, which accumulates the moving average of squared gradients. And this is the most widely used method today. It works very well. When you want to train something, you just, by default, you can use Adam. Now you can answer this question. Who is Adam? Adam, what is Adam? It is this 3 lines is Adam, okay? Adam W is a recent development, which is getting traction, a lot of traction, and people are using by default Adam W. And there's a slight difference between Adam and Adam W. It's about the regularization here. So suppose that your overall cost function to train a neural network has this form. It has a loss term defined over your training examples. So you want to minimize some cross entropy or regression loss, whatever, over your data points. But you also want to regularize your model. And you use this L2 norm, which minimizes the norm of the solution that you want to find. And this is a common practice, okay? Now, if you are not careful enough and you apply Adam to this cost function C, here I wrote the update equations for you below. This is plain Adam. And the regularization term might interfere with adaptive learning rates because we are accumulating the moving average of gradients and accumulating their square. And these two terms take into account the regularization tool. And that's why people have discovered that if you don't include this regularization L2 norm into Adam's momentum and squared cache, then it works better. And here is Adam W on the right. So it applies the momentum on the gradient of this loss only, and the squared cache, again, similarly only on the L, not C. But this part is reflected here. Because when you take the gradient of C, what is it? The gradient of L plus lambda theta, right? You know how to take a derivative. So, yeah, and this lambda theta is here. That's the only difference. The regularization term is taken outside of momentum and V calculations. That's it. And in practice, people say that this is working very well. And as I said, adaptive learning rate methods is an active research area. Maybe you have heard of Muon, a recent method that speeds up LLM training. You can check. It's a little bit more complicated than Adam and Adam W. There's a great video which I encourage you to watch if you want to learn about Muon. Okay, let's take a break here. 10-minute break. Okay, let's start. So finding the optimal learning rate is very important for your end result, but there's also learning rate scheduling. It's also important. And this is again, mostly trial and error. We know that it's good to reduce learning rate over epochs because this reduces the noise injected into training. But how you are going to reduce this is not very clear. We don't have clear recipes on this really, but there are choices. For example, you can use a step LR scheduler, which says, for example, every 20 epochs, you can reduce your learning rate by some factor. And these are hyperparameters. Right? You have to decide on these numbers. Similarly, you can also choose to reduce your learning rate on plateau, which means if the training loss curve on your training set is plain and it's not going down further, then you reduce your learning rate by some factor. This is what is called reduce LR on plateau. Another one is exponential LR scheduler. You exponentially decay your learning rate over epochs. But there are other more fancy things like the cosine annealing, and you can do this. You restart this several times. Like in here, cyclical learning rate scheduler. This is interesting because it not only decreases learning rate, but sometimes it increases the learning rate. And again, this is shown to be beneficial. And this is also an active area of research. And the figures are from the cyclical learning rate paper from 2017. As you can see, people are experimenting with keeping the magnitude of those cycles the same or reducing them and reducing them with an exponential decay and so on. This is, again, something to experiment with when you're training your models. Okay. So last week, when we looked at backpropagation, we looked at very simple cases where in one of them, we only looked at one single artificial neuron, and the other example, we have looked at two neuron examples. But as we know, the models are now giant, and we have to come up with a better way. And here we will talk about that. As you know, neural network is nothing but a composition of several linear and nonlinear functions. Y is the output of F1, F2, F3, and so on. And given a specific architecture that corresponds to a composition, one can easily write the gradient with respect to parameters, but a modular approach is desirable so that you know the derivatives of this specific module F1, and then you know the gradients of this specific module and that specific module, and then next time you create a new neural network, because it is like using Lego pieces to combine together, and now it's a new model. Now you don't want to spend too much time on computing the gradient of the new model, but rather you want to reuse the gradient of building blocks, right? And this is what we are going to do today here. So let's define a computing block as this diagram. There is an input X. The rectangle is like a system which processes the input, and it implements a function f with parameters w, and at the end it produces an output O. We can define the mathematical expression for this computing block as this simple equation: O is equal to f of x, semicolon w, right to the semicolon is the parameters of the function. We can talk about two different derivatives of this function computing block, derivative of output with respect to input, which is this, derivative of O with respect to X, or the derivative of O with respect to function parameters, okay? There are two different derivatives that you can talk about here. For simplicity, we assume that X, W, and O are scalars, but in fact, in practice, we are dealing with gradients, which is the vector of partial derivatives, and Jacobians, and these are matrices, right? But for simplicity, we will talk about single variables because it is easier to explain. Here's an exercise for you. Draw the computing block and write down derivatives for a fully connected layer with D input nodes and K output nodes, receiving N examples. So there will be D input nodes going to a fully connected layer. So this will be like that. And then there will be K output nodes from here. And there are N examples. Okay. And here is the solution, actually. The input is a N by D matrix because we have N examples with D dimensional feature vectors. The fully connected layer is characterized by a matrix multiplication. If we call this X, and the parameters of this is W, the fully connected layer basically implements X times W, and then the output will be N by K. Again here, if we look at the derivative of output with respect to input, it will be the parameters of the function. If you look at the output, derivative of output with respect to parameters, it will be the input to the function. But we should be really talking about the partial derivative of O with respect to an entry in the input matrix or an entry in the weight vector. So that's the proper way, but again, we are abusing notation here to explain, make things simpler. In fact, X is a matrix and W is a vector. Let's do the same for a ReLU layer receiving N by K input, and the output will be obviously N by K because ReLU does not change the dimensions of its input. So these are the same, sorry. So this and that are the same. And ReLU implements this function, as you know, max of 0 or X. What is the derivative of output with respect to input? So derivative of O with respect to X, what is it? There will be two cases, right? If X positive, then 1, otherwise 0, right? Something like this. What is the output, derivative of output with respect to parameters? Actually, this is tricky because the ReLU does not have any learnable parameters. So that's why this does not exist. We cannot talk about the derivative of output of a ReLU with respect to its parameters. So yeah, no parameters, nothing to learn. It was a trick question. I was tricked too. Okay, so well, it's easy. The derivative of max 0 comma x is this. Okay, now let's combine computing blocks. This is, yes.
Previous slide,
Mhm.
one before that. Sorry, the one before that. I thought, by X linear matrix, does it mean N by D or just?
Yeah. Yes, this is x. Mhm. Now we start computing, concatenating computing blocks. We have two blocks here, F1 and F2. Each has its own input and output, and each has its own parameters. In this two-block neural network, if you want to update W2, you need the gradient, you need this derivative, partial derivative of output 2 with respect to W2. To update W1, you need the partial derivative of O2, which is the output of the whole thing, with respect to W1. And as we know from chain rule, we can write this one as the partial of O2 with respect to O1 times partial of O2 with respect to W1. So notice here that each block has its own derivative with respect to input and derivative with respect to parameters. So each block has these two distinct types of derivatives. When you're backpropagating, be careful which one to use. If you want to update W1, here we are using at the end of the chain rule, it's the derivative with respect to parameters, but before that, it's derivative with respect to input. I think I demonstrated here. Now we have three blocks. Each has output O1, O2, O3. And if I want to calculate the derivative with respect to W1, I need to write down this derivative, right? Partial of O3 with respect to W1. And this is the chain rule, and derivative of O3 with respect to O2, derivative of O2 with respect to O1, and the derivative of O1 with respect to W1. So you change the derivatives with respect to input up to, so for this part, but when you are here, because the thing that you want to update is at that block, you write the derivative with respect to parameters here. So in the next slide, again, there's an exercise which I won't do it here. It will take time, but I included the solution. You can do this exercise on your own. It will be very useful. Let me just check my microphone. Okay. Here I'm asking the update, finding the update, gradient update vectors for a network like this. X is the n by d input. It goes through a fully connected layer, and then it goes through a softmax normalization layer, and then it goes through a cross entropy module computing block. That cross entropy also takes the ground truth labels, and there's of course a loss value at the end. So this is like a full MLP example actually with a real loss function. So you can work out this exercise, and the whole solution is actually on the slides. It is nice because you have to calculate the derivative of softmax, and then you have to calculate the derivative of cross entropy. And at the end, you have these nice results. Okay, you are encouraged to work on this exercise yourself. The solution has a few slides. Now we can start CNNs. After looking at topics related to MLPs and the optimization of neural networks, now we can look at convolutional neural networks, shortly known as ConVnets or CNNs. So who invented the CNN is again a discussion topic. There is a neocognitron network by Fukushima in 1980. But there is this technical report in 1989 by Jan LeCun, where he basically defines a convolutional neural network and solves the MNIST problem. Anyway, maybe it's not that important. CNNs are simply artificial neural networks that use convolution in place of general matrix multiplication in at least one of their layers. In MLPs, when you are implementing fully connected layers, you're actually doing general matrix multiplication. But in CNNs, we replace those matrix multiplication operations with the convolution operation, which you know from the signals and systems class, and maybe from other classes. Convolutional neural networks are suitable for tasks that has translation or time equivariance, and they are suitable for data that has a grid-like topology. For example, images has 2D, they are defined on a 2D grid, or videos on a 3D grid, or time series data, 1D, or even, it could be more dimensions, but it is defined on a regular grid. Then if something is defined on a regular grid, then you can do, theoretically, CNNs on them. As we know, multi-layer perceptrons, the layers are fully connected. It uses matrix multiplication to compute the next layer. CNNs have sparse connections as opposed to fully connected layers in MLPs. It uses convolution to compute the next layer, and everything else is common. Activation functions, cost functions, how you train them, how you backpropagate, these are all the same. The only difference is that CNNs use convolutional layers, and we will see its properties in a moment. In a supervised learning problem, COMNETs learn both the hierarchical representation of data and the decision boundaries on these representations, which we call the classifier, at the same time. So that's why they are very attractive, desired properties. In traditional pattern recognition, let's talk about image classification problem. You first extract features, and these are handcrafted features, and then you train classifier on them. An example for this would be extracting SIFT features, for example, on an image, and then training SVM classifiers on them. Early 90s, it was like that. SIFT or other local binary patterns, GIST features, SIFT features, there are many of them, and SVM. Later, you extract features. This is early 2000s. On top of them, you define these mid-level features, which are, for example, Fisher vectors or some kind of clustering you can do on top of your feature extractors. And still you use a classifier on top of them, which is support vector machine usually. But in deep learning since 2012, this is the approach. Your early layers of the network learns low-level features, mid-level features learn intermediate level features, and then at the end you have a trainable classifier, and a box being red here means it's learnable. In deep learning, everything is learnable, but in the previous approaches, feature extraction was handcrafted. It was not learnable. Mid-level features as well. So this is the difference that deep learning makes. And here's a visualization from a work in 2013. This is a data set. This is a model trained on ImageNet data set. And here are the visualizations of the neurons, convolutional neurons in the early layers. They are like edge detectors. Convolutional neurons in mid-level layers, they are like junction and corner detectors, so they combine edges. And high-level features, now we begin to see objects and object parts. They are more complicated things. So honeycomb, a bird maybe, things like that. A wheel of a car maybe, yeah. Well, this is a very nice story, but we know that this is not the whole story, and we still need to understand it a lot. There are things that we don't understand. For example, CNNs trained on ImageNet are biased towards texture. And increasing their shape bias improves their accuracy and robustness. And in this 2019 paper, there's a very striking experiment. They took two images, the ones on the left. The first one is a close-up elephant picture. It's the skin of an elephant, so it's a texture. It's the texture image. And the second one is a cat. And using style transfer methods, we did not see them, but think of them as a method to combine these two images. And you get the third image, where when you look at this image, you still see the shape of the cat, but if you look at the texture, it's the elephant skin texture. And CNNs, what do you think give a prediction for the third image? They say it's an elephant skin. They say it's an elephant, okay? But humans say that this is a cat. So, although the visualizations here draws a very nice, paints a nice story, saying that edges are detected first, then their combinations, and then more complicated parts. It's not the whole story, okay? It's not, it doesn't hold true for these large models because they take shortcuts actually. To solve this classification problem, the model finds out that detecting the texture and deciding on texture gives you good accuracy, but it's in contrast with how humans perceive and recognize objects. So again, what it learns through layers is there's a nice story, but we need to still understand it further. This paper says that it is actually concentrating on texture instead of shapes. Again, active area of research, and this is also what I'm interested in, what kind of representations these models learn and how we can steer them towards human-aligned representations so that we increase their robustness and out-of-distribution accuracy. Okay, convolution operation, you all know from signal and systems classes, it is this defined like that in continuous domain and discrete domain. If you notice, this is a sliding dot product, and we use these operations to extract information from a signal. We extract information from the signal X, which is input, using something we called filter, the W here. But the definitions here are actually the definitions of the correlation operation, not convolution. And the reason I'm showing this first is that in modern deep learning libraries, what they call as convolution is actually a correlation operation. Okay, I don't know, it's a misnomer. The naming convention is, we call X the input, we call W as the kernel or filter, and this carries out this operation and it outputs a feature map, what we call a feature map. And this part computes the similarity of two signals, X and W. Therefore, it can be used to find patterns using template matching with normalized cross correlation. So whatever structure your filter has or kernel has, those structures in X will be emphasized. So they will be extracted and the dissimilar patterns will be suppressed. Okay, here is convolution. As you might remember from your signals and systems classes, convolution, we have this minus A, which flips the kernel, but in correlation, you don't have that. And these are identical operations. If the kernel is symmetric, then these two are the same. And both are linear shift invariant operations, which results in nice properties such that if you know the impulse response of the filter, then the whole system is characterized by the impulse response. But we don't use those facts actually when training CNNs. And here is the 2D version of cross correlation. Again, you can call this now an image because it's 2D, and you can call this as a kernel or filter, again 2D. And this is the operation that it does on the image. And many machine learning libraries actually implement this operation, and it is cross correlation, but they call it convolution. So when you look at a convolutional layer, it is actually implementing a cross correlation operation, this specific operation. This might be a too simple example for you. We have a 3x4 image on the left and a 2x2 kernel. What we do is we overlay the kernel on top left and take an element-wise product and sum them. This is the definition of dot product. And this is the output at the first location. And then you move your kernel to the right, one location, 1 pixel. You compute this. You repeat the same operation, which is dot product. And this goes on like that. This is what convolution does. Let's look at an example, a real example here. This is, if you took image processing, this is called the Sobel operator. And this is an edge detection filter. Look at the shape of the Sobel operator. There is a positive column on the right, there's a negative column on the left, and there are zeros in the middle. So it has a vertical edge structure, right? Positive, negative. It's a vertical edge, and it will emphasize, if you apply it to an image, it will emphasize vertical edges. That's why we say that convolution is pattern matching. And let's look at the result of this. For this bicycle wall image, if you apply the vertical Sobel operator, the vertical edges here are emphasized, as we can see, and so on. But if you apply the horizontal Sobel operator, which is this, the horizontal edges are emphasized, right? So notice that no edges are found here because at that location, we only have vertical edges in the input image, and the horizontal Sobel operator just does not find any edges there. And then you can find the oriented edges as a combination of these two outputs of these two filters. Multi-layer perceptrons were good, and they are universal function approximators. Then what is the reason using CNNs, right? MLPs will solve everything, right? Theoretically, yes. But why do we use ConVnets? Because there are very good motivation behind it. There are 4. First is sparse interactions. As you know, multi-layer perceptrons are fully connected layers, but CNNs are locally connected. Each convolutional neuron only looks at a small portion of its input, so it's locally connected, and therefore it's also sparsely connected. It is not connected to every pixel in the input image. There is parameter sharing, which greatly reduces the number of learning parameters. There is equivariance property, which is good for things like edge detection, object detection, segmentation, and the ability to process inputs of variable sizes. The first one we achieve using localized neurons. So it only localizes into some spatial area. Parameter sharing is when you use the localized neuron, the same neuron at different locations. The parameters are shared. And the input, if the input moves, you take a video of a car moving, the convolutional features of that car also moves the same amount in the output. This is called equivariance. And ability to process inputs of variable sizes is achieved by using scalable pooling regions. And we will talk about pooling in the upcoming slides. So now we are going to look at these four properties one by one. The first one is sparse interactions. In a usual ANN, the artificial neural network is actually sometimes synonym for MLP, but in a usual MLP, the nodes are fully connected. So this node is fully connected to everything in the previous layer. But in a CNN, this node is actually only connected to this. Okay, or similarly, this node is only connected to 3 neurons, whereas the same thing here is connected to everything. Okay, so fully connected versus sparsely connected, and also locally connected. So S4 is locally connected. It's not connected to a neuron in the previous layer that is far away from S4. So this is just a demonstration of the sparse interactions. You have a 4x4 image, 2x2 kernel. You start from the top left and then move it towards right. And then once the first row is done, you move 1 pixel below and repeat. And this is how the computation of CNN or convolution is done, and it is accumulated in the output. And this sparse interactions drastically reduces number of learnable parameters. And let's see it over an example. So consider a layer with m-dimensional input and n-dimensional output. Okay. What is the time complexity of such a fully connected layer? Time complexity means as these numbers m and n goes to infinity in the asymptotic notation, if these are approach very large numbers, how does the number of operations carried out by the fully connected layer scale? So what is the number of operations that a fully connected layer with m-dimensional input and n-dimensional output is? So how many operations does it do? M multiplied by n, yes. So it's in the order of O, M, N. This is asymptotical notation. So CS people knows this. What about the sparsely connected layer, which is like a CNN? Here we have to, of course, need another information. The number of elements in the filter is K. Again, we have m-dimensional input, n-dimensional output, but we want to compute this using a sparsely connected layer, a convolutional neuron, let's say. And this neuron has, in its filter, K elements. What is the number of operations? So this is M, this is N, and we have a K-dimensional filter which takes this and then computes this one. Yes, you are right. This will be O NK. And if you compare OMN and ONK, they will be drastically different because the filter is usually much smaller than M or N. M and N are usually in similar size, but the filter sizes are usually very small, and that's why you see the great advantage of using convolutional layers. Yes, we typically, K is much smaller than M, and if you compare these two, the advantage of sparse connections is evident. Here is the same example, but with numbers. Let's say our image is 200 by 200. And we want to compute 4K hidden units out of this image. If you use a fully connected layer to do that, you need about 2 billion parameters. But if you use locally connected or sparsely connected neurons, again, for the same image, 200 by 200, and you have 40K of these, so you want to compute 40K hidden units out of this image with a filter size of 10 by 10, then you have 4 million parameters. So 2 billion versus 4 million. There are orders of magnitude difference. That's why we like CNNs. Number of learnable parameters are drastically lower. The second motivation is parameter sharing, which means you apply the same neuron, which is locally connected, to all different locations in the input image, because you slide it on the image, right? It's a sliding window operation. So the same kernel filter applied to everywhere on a layer. The number of total parameters to be learned and the storage requirements are dramatically reduced because you just learn the parameters of a single kernel, and it is applied to all locations in the input. Here, the same neuron, let's say it sees 10 by 10 location. It has some weights in it, and you apply it to all locations in the input image. The number of learnable parameters is greatly reduced. Third motivation is equivariance. And mathematical definition of equivariance is as follows. F of g is equal to g of f. So that means you can change the order of functions that you apply. And we know that convolution is commutative with translation. Mhm. Mhm. Okay, the question is, CNNs has a smaller number of parameters to learn, but which one has better accuracy? Depends on the problem. If it's an image classification problem, CNNs are always better. Not always, but usually better. But if you are working on, let's say, tabular data, the conventional database like tabular data, then probably MLPs will be better. So it depends on the problem. So equivariance, there's a relation between translation and convolution. So let me show the what we mean by equivariance. So if you apply a shift to this object and the object moves to from top left to bottom right, and if you apply convolution to those two images, the output of convolution moves in the same amount, in the same direction and in the same amount. And this is called equivariance. This is good because when you want to detect edges, let's say you want to detect a vertical edge in the image, you don't need to design a specialized operation per location, right? You just need to define what a vertical edge is, and then you apply it to everywhere in the image. Or object detection. You want to detect a car, and your filter will work whether the car is on the top left of the image or bottom right of the image, doesn't matter. It will detect the car. And this is called equivariance. MLPs don't have that, right? So notice that if you apply the same MLP to this image and to that image, you will get entirely different results. But if the task were to recognize this object. I forgot its name. It's in chess. What is it? Rook? Rook. Rook. Okay. If your task is to recognize chess pieces, and this is the rook class, and its location is not important, let's say, then CNN with a pooling layer, with a max pooling layer, we will talk about max pooling, will work much better than an MLP, because in MLP, it will calculate a different feature vector for the left image and another different feature for the right image. Okay, so that means you need lots more data for MLP to model this problem. Okay, so it depends on the task. And finally, CNNs have a good property. They can process arbitrary sized inputs, but a fully connected layer only accepts a fixed size input vector. Let's say you are working on an image data set and your images have, some of them are small, some of them are large. You can still process them using the same convolutional neural network, but if you want to use an MLP, you first need to make them the same size. Otherwise, it won't work. Okay? Okay, next we will talk about pooling, but after the break. Okay, let's take a 15-minute break. Okay, let's start. We have two topics left for convolution. One of them is pooling, the other is padding, and we can quickly learn them. And after that, we will look at AlexNet, a real ConvNet from literature, and then we will be done for today. So in a convolutional layer, typical convolutional layer, the convolution stage implements an affine transform because it's a dot product is a linear operation, and you may use a bias term or not. So x times w plus b, this is optional. So it's an affine transform, and then you apply a nonlinearity such as rectified linear unit. And then after that, we do something called pooling, and let's now look at what pooling is. A pooling function takes the output of the previous layer at a certain location L and computes a summary of the neighborhood around L. This is what pooling does. For example, max pooling introduced in this paper from 1982, and there is biological motivation for that. In the V1 area of our visual cortex, which is at the back of our brain, there are V1 simple cells and V1 complex cells. V1 simple cells are simple edge detectors. They prefer light stimulus at a certain orientation and a certain stimulus intensity. And if you shine the light at a certain location and orientation, it will fire. But V1 complex cell, on the other hand, keeps firing even if you move the oriented line slightly to the left or right. So it has a receptive field where if the intensity, if the stimulus is within that region, it will just fire. And this is similar to what max pooling does. Within an area, you just take the maximum, and then this is what it is achieving. So we can say that V1 complex cells are actually implementing max pooling, and there is that biological motivation for that. To show how max pooling works, these neurons are, let's say, the input layer, and this layer implements the pooling stage, max pooling, and each neuron is connected sparsely to the input. And this one, for example, specifically, takes input from 3 neurons, and it takes the max over them. So 0.1, 1, 0.2, max is 1, and that's why it's 1. And the other neurons in the pooling stage carries out the same operation. If you move the input layer to the right 1 pixel, so I take this input layer and move it to 1 pixel to the right, the pooling stage output, only half of the values change in the output layer. Therefore, we say that max pooling introduces invariance. Remember the rook example that we have seen? The chess piece is here, or it was there. If you implement a convolutional layer on top of this image and put a max pooling layer after that, we can design a CNN that can recognize chess pieces regardless of where they are. So max pooling achieves that. So pooling summarizes. We can make a sparse summary by using a stride larger than 1. Stride means distance between neighboring neurons. So this one receives input from 3 neurons, but the next one receives input from these 3, and there is now a stride of 2 because in between them there are 2. So it moved 2 steps, not just 1. This is called stride. This is how you implement dilated convolution. We will see it next week. But this reduces computational complexity and memory requirements. So pooling invariance to local translation can be a useful property if we care more about whether some feature is present than exactly where it is. Here's an example. Let's assume this local convolutional neuron or filter is an eye detector. So it has certain pattern in its parameters where when it is convolved with an eye, it gives a high response, otherwise it gives a low response. And if you slide it over the image, so one of them will give, probably this one will give a very high response, the others will give low responses because this one overlaps with the eye perfectly. But on top of these, if you put a max pooling layer, then you get a response where within this large region, whether there's an eye or not, the max pooling will give you that answer. Okay, you can use pooling for other transformations as well. For example, if you have different channel which detects the orientation of your input, and if you take a max pooling on top of that, then you achieve invariance to rotation as well. Okay. Usually we use spatial pooling to produce invariance to translation, as in the chess piece example. But if you have something that detects rotated objects, and if you put a max pooling layer on top of that, now you achieve invariance to rotation. Okay. An example is from this 2013 paper. Another use of pooling is you might want to classify images of arbitrary sizes. In your data set, let's say you have images of 100 by 100 pixels and 500 by 500 pixels. If you apply the same CNN on top of these images, the feature map you get will be proportional to the image size. Right? The one with the 100 by 100 will give you a smaller feature map. The image with 500 by 500 will give you a 5 times larger feature map. And this is a problem because the input to the classification layer, which is implemented using fully connected layers, MLPs, must be of fixed size. Now you have a 100 by 100 image, and you have a 500 by 500 image. They will produce different feature vectors after a convolutional layer, and you want to classify them using the same network, then you have to somehow change their size of the feature vector, right? And pooling is a way to do that. For example, you can define 4 regions on the image, 4 quadrants, and then for each quadrant, you apply a pooling. It could be average pooling, it could be max pooling, it could be even learnable pooling, which we'll see in transformers. And for each region, you get a fixed dimensional feature vector. And since there are 4 quadrants, you get 4 times the fixed dimensional feature vector. And now, regardless of your input image size, you now have 4 times this whatever pooling gives you. Okay, so this is how you can handle images of arbitrary sizes using pooling. Any questions up to now? There is also learnable pooling. More on this in the self-attention transformer chapter later. Let's talk about padding too, because in convolution, there is this important definition, padding. So if you apply, let's say this is a 1D image in the input, and we are processing this input image with a filter of length 6. So this one is actually connected to 6 pixels in the previous layer. And then you can choose to apply your filter so that the filter remains always within the image. And this is called valid convolution. There's a terminology in padding. This is called valid convolution. But if you do that, and if you keep doing that, you will reduce the output size progressively, right? But if you want the same size of output as the size of the input image, you can use same convolution, which will pad the input with zeros or any other value of your choice, but usually zeros are used. So you pad, that means you add these additional 0 entries and then apply your length of 6 filter on that. Now the input size and the output size are the same, but here it was, the output size was reduced. Okay, so there is valid convolution, same convolution, and also full convolution. So I like to encourage you to check PyTorch's convolution and padding layers. I mean, not layers, padding settings in its documentation. So yeah, this was padding, and our last topic for today, assuming no questions about padding. Yes. Yes.
For rotational variance and spatial variance.
Yes, because if you apply max pooling, what it does is take the maximum of things in its input. And in that input, it could be coming from spatial detection of the chess piece, or it might be something that responds to the rotated orientation of the chess pieces. So it relates to the previous layer actually. If your previous layer computes orientations and if you put a max on top of that, you achieve invariance to rotation. Okay. So yeah, the magic is not in the pooling layer. It just takes a max or average. But in the previous layer, if you do detect rotations, that's the important part. Now let's look at a famous COMNET from the literature, which is AlexNet. This is the 2012 paper, which started the deep learning revolution on ImageNet challenge. Today, it has more than 148,000 citations, and it keeps growing. And this is the figure that shows the AlexNet architecture. It looks complicated. Well, it was complicated because AlexNet was running on 2 GPUs on parallel. So it's an architecture that has some part of it is running on GPU 1 and the other part is GPU 2. So processing in different GPUs are connected at only some layers. So for example, here, the parallel stream coming from GPU 1 and GPU 2 are exchanged, interconnected at the end. And it's not a very deep architecture. It has 5 convolutional layers and at the end 3 fully connected layers. And each convolution layer consists of convolution, obviously, a nonlinearity, which they use ReLU, a normalization operation, and max pooling. And here you also see the parameters of the each convolution layer. For example, the first one has 11 by 11 filters. The size of the filter is 11 by 11, and they work at a stride of 4. So every 4 pixels, you apply 11 by 11 filters. So these are very, specific choices, right? And this is these are the values that are chosen after a very rigorous hyperparameter tuning. They really optimized all these numbers. In the second CNN convolution layer, the filters are 5 by 5. In the other one, it's 3 by 3 and 3 by 3. And the first convolutional layer outputs a 48 dimensional. So in the first convolutional layer, the RGB image is the input, and there are 48 channels in the output. So there are 11 by 11 filters, and there are 48 of them, because each of them contributes a channel here. So after convolution, there is ReLU. Now let's look at normalization. We know what max pooling is. Normalization in AlexNet was this complicated formula. In summary, what it does is, so first of all, what is being averaged out here is the ReLU output of kernel I at location xy. You average them over this neighborhood, which is the adjacent kernels or channels at the same spatial location. So this is a very specific kind of normalization. We will see other types of normalizations, but in AlexNet, we don't use this today, really. They chose to use this local response normalization over the adjacent neurons. And these, look at how many parameters it has. K, alpha, I don't know, beta, right? And these are all optimized by the hyperparameter tuning method, whatever that was. And they found that this normalization improved results. AlexNet, if you look at the simplified architectural diagram, the input is at the bottom and the category prediction is at the top. This is for image classification, as you remember. On the left, you see the total number of parameters. It's 60 million. On the right, you see the total number of floating point operations. So each convolutional layer, for example, the first one, look at that. It has 35K learnable parameters. And compare this with the number of learnable parameters in the fully connected layers. They are in the order of millions. Fully connected layers are dense. That's why it's millions. but conv layers are small, 35K, 300K. But again, compare this with the total floating number of operations, number of floating point operations, and compare them with the flops of the fully connected layers. So convolutional layers have smaller number of learnable parameters, but they are comparable or even more in terms of number of floating point operations. You can see this why, right? Because of parameter sharing. Because of parameter sharing, the number of learnable parameters is small because you apply the same filter at all locations in the image. This is what increases the number of floating point operations, 105 millions, but it keeps the number of learnable parameters low. So this was AlexNet. Importantly, to reduce overfitting, AlexNet used two regularization methods. The first one is data augmentation and the second is dropout. Data augmentation is any transformation that preserves the labels of your training set. If you apply a transformation to your input and that transformation does not change the label of your example, then it's called data augmentation. It's a label preserving operation. And they use translations, random translations. And the images were 200 by 56 pixels. Within that image, they choose from random locations 224 by 224 crops. And they choose this location randomly, and this is achieves translation augmentation. Because it slightly shifts the object to the right, left, and top and bottom. This, they also applied horizontal reflection. So put a mirror here and take the reflection horizontal. It will still be the same object, right? So, but they didn't apply vertical reflection because when you flip something vertically, for example, faces, you cannot recognize faces. It is a drastic thing. They didn't, of course, use it. And this is because physics of the world, the light is mostly comes from above, and we have gravity, things sit on the ground, right? So that's why if we take vertical flips, it's something else. It's probably not a label preserving transformation. But horizontal is no problem. Also, at test time, they applied these translation augmentation by extracting 5 224 by 224 patches from the four corners and from the center. And they applied horizontal reflection as well. So 10 patches in all. So during test time, you take a test image, you extract these 5 patches from four corners and center, and take horizontal flips of them. So you get 10 different images out of one test image. And you apply your model to these 10 examples, and then you take averaging the predictions made by the network softmax layer on 10 patches. So you basically average the probabilities output by these 10 different images. This is called test time augmentation. Another data augmentation they use is to play with the RGB channels of the images. They take the multiples of the principal components of RGB distribution of training images, and then they add along this principal component of RGB distribution, they add small changes to each image, and object identity is preserved, right? Object identity is invariant to changes in the intensity and color of the illumination. And applying this augmentation reduced the top one error by 1%. And 1% is a significant thing in that data set. The other regularization that they used is dropout. And this is a type of ensembling method, actually. We know that from ensembling idea in machine learning that combining the predictions of many different models is a very successful way to reduce test error. So we know that ensembling is a good thing, but ensembling big neural networks that already takes several days to train is not a practical thing. You cannot create several different versions of AlexNet and train them separately. It will take a lot of days. If you could do it, it would be good to ensemble them, but you cannot do it. The practical way to do ensembling is dropout. And here is what you do. I will just show you the what it does in the figure. On the left, you see the standard neural net, which shows two fully connected layers. Everything is connected to. So this one is connected to all. You have the full connections. But if you apply dropout to this during training, dropout is applied during training, you randomly kill some of the neurons. And these crosses here means this neuron was killed during that specific training iteration. Now, you do this at every iteration randomly. So each training iteration, you kill a subset of the neurons randomly, and this gives you a specific architecture. In the next iteration, maybe this neuron will be killed, and it will correspond to another architecture, right? And by doing that, the neurons cannot rely on co-adaptations. So as a neuron, you cannot rely on the whether some specific neuron in your previous layer or in a friend in your current layer, you cannot rely on the existence of that neuron all the time because sometimes it is killed. Yes.
Doesn't this make the model unreproducible?
Unreproducible. Yeah, that's a good question because at every training iteration, you get a different network actually, but it is pretty reproducible. It creates a variance in the results, but that variance is not that high.
So they always converge.
Yes, yeah, it works. So during training, you kill P% of the neurons. This is a hyperparameter in dropout. And then do the training with the surviving neurons. And then during test time, you don't drop any neurons. But to ensure the response magnitude is the same in expectation, you need to multiply their outputs by P. And this was the dropout probability you used during training. So dropout is a good regularization method, and it is a way of ensembling different architectures. It's actually approximation to taking the geometric mean of the predictive distributions produced by the exponentially many dropout networks. But disadvantage is that dropout roughly doubles the number of iterations required to converge because during training you are killing maybe half of the neurons, and this will take a larger training time to complete. Hmm? In what? Any models that uses dropout in test time? Good question. I don't know.
I heard about something called Monte Carlo dropouts, which is
Monte Carlo dropout. Okay. Yes, you are right. I think it is used in uncertainty estimation. In the deep ensembles method, you train different versions of the same network and make an ensemble. And then you give an input to all of these networks. and all of them give different probabilities, and you measure the variance in the probabilities, and this is a estimation of the uncertainty of the network. But there might be other methods that apply dropout during test time that I don't know. Yes, it gives better results than the single network, but it's costly. Ensembling is costly. Any other questions? Okay. So finally, please check out the Colab notebook that is on the web. It is on. Remember, I went over the Colab notebook on MLPs at the beginning today, and this one is a similar notebook that is on CNNs. It's the same, actually, solving the same problem, but now you see how a CNN is defined using PyTorch, how it is trained, and so on. So I encourage you to play with the numbers here. Change these numbers in the CNN, apply dropout, things like that. Okay, so try to get a sense of how CNNs are trained. Okay, I think that's it for today. Now let me give you the quiz. So I'm asking a very simple question. Write down the pseudocode for SGD. But try to do this without looking at anywhere and try individually, okay? It's a very good exercise. You think that you know it, but if you try to do it from memory, it could be difficult, but yes, try to do it on your own.